Hey there, and welcome. Today, we're diving in and unlocking the power of exponents. I know they can look a little intimidating with those tiny numbers floating all over the place, but trust me, by the end of this, you'll see they're just a super efficient way to write down some really cool mathematical ideas.
Does a seam like this look a little too familiar? Just a total jumble of formulas and symbols? It's so easy to feel lost in all that. But our mission today is to cut right through the noise and turn all that confusion into pure confidence. We're going to make sense of it one simple property at a time.
So, here's our game plan. First, we're going to tackle the so-called oddballs, zero and negative exponents. Then we'll build up our main toolkit with the core properties. After that, we'll see how they work with bigger combinations. And finally, the really fun part, we'll put it all to use with some amazing real-world examples. Sound good? Let's get started.
All right, first up, let's get a handle on the two rules that honestly trip a lot of people up. But think of them less as weird exceptions and more like little puzzles that have surprisingly simple solutions. Once you see the trick, they'll just click. Okay, here's our first rule, the zero exponent. And you're going to love how simple this is. Any number, and I mean any number, as long as it's not zero, raised to the power of zero is just 1. That's it. 5 to the power of 0, 1. 999 to the power of 0, it's 1. It's one of those fundamental rules that just cleans up a ton of equations. So what's the deal with negative exponents? This is another one that feels a little strange at first. Now, the big trap people fall into is thinking it makes the number negative. It doesn't. A negative exponent is actually an instruction. It's telling you to flip it. It means take the reciprocal. So a to the power of negative n just becomes 1 over a to the power of positive n. You're basically just moving it to the other side of the fraction line.
Okay, let's see this in action. For part A, we have 6.7 to the power of 0. Well, what's our rule? It's just 1. Easy. Now for B, we have negative 2 to the power of negative 4. That negative exponent tells us to flip it, right? So it becomes 1 over negative 2 to the power of positive 4. And negative 2 times itself 4 times, that gives us 16. So the final answer is 1 over 16. See? Once you know the rule, it's not so bad.
All right, it's your turn to try. Take a look at this expression right here. How would you clean this up using only positive exponents? Go ahead and pause here and give it a try. Just remember what those negative exponents do and what happens to anything raised to the power of 0. Awesome. Now that we've got the oddballs sorted out, let's get to the main event and build the core of our mathematical toolkit. These next three properties, well, these are the real workhorses. You're going to see them and use them absolutely everywhere. So picture this. You've got two powers, and they share the same base number, like, say, 7 to the power of 2 and 7 to the power of 4. And you need to multiply them together. What's the shortcut? Is there an easier way than figuring out both and then multiplying?
Of course there is, and it's called the product of powers property. It's super straightforward. When you multiply powers that have the same base, you just add their exponents together. That's it. So 4 to the power of 6 times 4 to the power of 3 just becomes 4 to the power of 6 plus 3, which is 4 to the power of 9. So much easier. Okay, so what if you're dividing instead of multiplying? Well, the logic here is just perfect. If multiplying means you add the exponents, then division, which is its opposite, must mean you subtract them. And that's exactly right. This is the quotient of powers property. As long as the base is the same, you just subtract the bottom exponent from the top one.
Let's add one more little wrinkle. What do you do when you run into something like 3 squared, and that whole thing is raised to the power of 5? You've got a power that's being raised to another power. How on earth do we simplify that?
And that is where the power of a power property comes into play. In this situation, you multiply the exponents. The big clue here is the parentheses. When you see a power inside parentheses being raised to another power on the outside, you just multiply them. So 4 to the 6th to the 3rd becomes 4 to the power of 6 times 3, or 4 to the 18th.
All right, let's see these three properties do their thing in a couple of quick examples. In part A, we're multiplying, so we add the exponents. 2 plus 6 is 8. Simple. For B, we're dividing, so we subtract. 2 minus 7 gives us negative 5, and we know what to do with that. We flip it to get 1 over negative 4 to the 5th. And in C, we have a power of a power, so we multiply. 4 times negative 3 is negative 12, which becomes 1 over z to the 12th.
Okay, time to level up a little bit. We've got the core rules down. Now let's see how they help us tackle stuff that looks a bit more complicated.
Specifically, what happens when you raise a whole group of things, or even a whole fraction, to a single power?
So check this out. We've got two more super useful properties here. First, the power of a product. If you have a bunch of things multiplied inside parentheses, and that whole thing is raised to a power, that exponent on the outside gets applied to every single piece on the inside. It kind of distributes itself. And the exact same logic works for the power of a quotient. If you've got a fraction raised to a power, that exponent goes to both the top and the bottom. It's a really consistent rule that helps simplify things a lot.
So, we've spent all this time building this amazing mathematical toolkit. But what's it actually for? Well, this is the payoff. Let's see how all these abstract rules are actually crucial for solving real, tangible problems out in the world.
Okay, here's a classic geometry problem. We need to find the volume of this cylinder. But there's a catch. We're told that its radius is always exactly half of its height. So how can we write a formula for the volume that only uses the height, h? This is exactly where our new exponent rules get to be the hero. Let's break down how we solve this step by step. First, we start with the basic volume formula we all know. Second, we do the substitution. We replace r with h divided by 2. Now step 3, this is the key moment. We use our power of a quotient property on that term. That lets us apply the square to both the h and the 2, giving us h squared over 4. And finally, we just tidy it all up. See how that one property was the critical move?
Now, for something I think is just incredibly cool. Scientists use exponents all the time with scientific notation because it lets them work with gigantic or microscopic numbers. Get this. This jellyfish releases a flash of light with about 1.25 times 10 to the 8th photons. But it does it in an insanely short amount of time, 6.25 times 10 to the negative 4th seconds. How many photons is that per second? Well, we have to divide.
So to figure this out, we're going to divide the regular numbers, and then we'll use our exponent rules for the powers of 10. That means we have 10 to the 8th divided by 10 to the negative 4th. Our quotient rule says we subtract the exponents. And here's where it gets cool. 8 minus negative 4 is the same as 8 plus 4, which is 12. So our final answer is going to have 10 to the power of 12.
And there you have it. That jellyfish pumps out 200 billion photons every single second. That is just a mind-boggling number, and we figured it out, nice and clean, because we understand how exponents work. That's why this stuff matters. It gives us the power to understand the universe at its most extreme.
All right, so let's do a quick recap of the awesome toolkit we've put together. When you multiply powers with the same base, you add the exponents. When you divide, you subtract. For a power of a power, you multiply. And when you have a power of a product or a fraction, that exponent just distributes to every part inside. These 5 properties right here, they're your foundation.
So look at that. We went from that chaotic chalkboard to having a clear, powerful set of tools. From just simplifying equations all the way to calculating the light from the jellyfish, these rules give you a whole new way to make sense of the world. So I guess the only question left is, what complex problems are you going to solve with them?